To get started here, I just want to welcome everyone again. My name is Silvio Perez. I'm the simulation product manager here at Hawkridge. I focus more on the structural side of things, but definitely versed in the other analysis products like flow simulation and plastics that you may have seen on the previous week. But before we get into that, this is part two of the road to validation, now focusing on the structural study. Last week, if you joined us, you saw part one, which was presented by Damon Tordini, who was talking about the capabilities of flow simulation. So here, really the goal is to really see how we can connect the dots between using those results from flow simulation into the structural analysis. But we'll get into that a little bit more in depth here in a few slides. But again, the main point of the series, if you've joined us or if this is the first one you're watching, we've developed the series in terms of showcasing all of the analysis products that we have available. And really what we want to show you or prove to you is really answering that question is the same analysis tool right from day one to day 100 or throughout the entire process of from conceptual design to actually manufacturing and producing this and delivering it, if you will. So pretty much we want to show you that we do have options to kind of help you throughout that entire process from initial design to final design, right? And here at Hawkridge we offer a variety of different tools. From what you may have seen last week, our computational fluid dynamics tool. That is a great tool to see just fluid behavior in addition to running a thermal analysis to see how hot this is going through those flow channels of the model. Or, again, being able to do a structural analysis here where, you're mainly just concerned about, how strong this is going to be. But sometimes those things overlap. Sometimes we may need to know one element of it first and then throw it over to another type of analysis. And that's really what we're going to do here and really show you that we have the capabilities to help you out from day one or day 100, so to speak. Right? So, and in addition to that, we're not just limited to just the analysis tools or, the simulation tools that we have. We have a pretty extensive portfolio here, as you can see, and it all stems from adopting your SOLIDWORKS CAD. Right? Everything here, for the most part, is integrated within the CAD software where, we can manage the files with our PDM tools, or if you're in doing some electrical type of design, then we can incorporate that as well. We have nice tools to be able to communicate that information, being able to do, instructional type of documents through our composer tool. And then you see that we have the validation side, which is what I primarily focus on, and we have capabilities to even prototype that with our 3D printing tools. So again, we have a pretty large array of different things that we can pretty much help you from day one to that last day of production to really make sure that you guys are being more efficient with your tools, being more efficient with your designs. So when we narrow down the offerings for simulation, it really comes down to these 5 steps. And we start off with our, our free offerings, if you will, where we have a good amount of different simulation videos on our YouTube channel. We have a whole bunch of different blogs that are related to simulation from, again, our computational fluid dynamics tool to structural. Pretty much we're always trying to develop more content to deliver to you to make sure that you guys are aware of the capabilities of the tools and how they can help you in your real life scenario. So definitely check that out. Check out our YouTube channel. You can just Google Hawkridge Systems YouTube. It should be like the first thing that pops up. Or you can reference our website. There's a lot of great resources there that kind of link to those videos as well. Moving forward, we have offerings here for technical support. Hopefully, for those of you who are aware of it, you guys are utilizing it. But we have degreed engineers that are able to help you with not only your CAD, but if you have the simulation tools, they can help you with that as well. So you're not really jumping through different hoops really to get one answer. You can talk to these individuals who are very familiar with the software and how it can help you out in the long run, right? So, and as far as your own development, getting familiar with the tools, we highly recommend doing training for these different softwares. even though the tools itself are pretty intuitive, easy to pick up and learn, especially through the tutorials that are embedded with the software. Having this training through us, the degreed engineers, is really helpful in really knowing the ins and outs of what we can do with the software. But of course, if you've taken any training, you know where the buttons are, you know what things are doing. But once you get to your actual model, it's like, okay, now what? How do I actually get started, or what's the best way to approach my specific problem? Well, that's where we can get into these flight plans or these consulting aspects where we do offer consulting and mentoring services to help you, to guide you in setting up a problem correctly with your specific model. So, or you may not have the resources or the time to actually do that, and that's where our consulting side comes into play, where we have experienced, again, engineers using this tool day in, day out, so you can leverage that and leverage that and help you accomplish or finish a project to completion. So if you have any questions with that, as far as what our consulting offerings are, definitely feel free to hit me up or shoot a message here, and I'll be able to help you with that. But now going into the actual case study here. So if you joined us last week, or if this is your first week, here's a little recap. The previous case study from last week, part 1, was talking about, again, our flow simulation tool, which is our computational fluid dynamics tool, which again, it allows us to see what the fluid behaviors are in addition to what the thermal distribution is due to that fluid flow. So what Damon Tordini did last week was he ran an analysis on this nozzle and this filter neck adapter that you can bolt on, and he wanted to see what the nozzle shape would do to the fluid pattern. So he did a comparison between an open flow versus one that was a little bit more restricted, and he wanted to see whether what the flow patterns were. In addition to that, he was able to see how hot the nozzle was getting after a minute of operation. So he was able to see what the temperature distribution was, not only of the fluid itself as it was flowing through the actual nozzle, but the temperature distribution that's happening through the actual geometry. So it really showcased very well how we can get this level of information of not only fluid behavior, but of the thermal side as well. So what I want to do now is, if we're documenting this flight log, is what we're calling it, is stage 1 was seeing, should I run it with that restrictor or not? Should I do this open flow? And, depending on what your design criteria are, we're able to simulate that and pretty much give a green light saying, all right, this design is okay. But there may be more to this. We are running something that's hot through the system, a hot fluid, and there may be some thermal stress concerns there. Or if we're continuously running this fluid through the system and constantly stressing the model, is it going to fatigue after a certain number of cycles or after a certain number of uses? So we can't get that level of information directly from flow, but we can transfer the information that we learn from flow simulation into our structural analysis. And that's really what we're showing here, is that we can leverage both softwares, and we can interact with them and get valid information to help you in your design. So stage 2, which is the structural, we're going to run a thermal stress analysis from the temperatures that we got from the flow simulation study. So I'll show you how we can transfer those results. And then we'll run that analysis, and then we'll be able to see whether this is going to survive just that instant and whether it's going to survive after a certain number of uses, certain number of cycles. Right, so that's the goal for today. Again, here's just more an illustration of all the packages that we offer that relate to our analysis tools, kind of the family of analysis tools. And today, again, we're going to be focusing on now the FEA, the finite element analysis tools, which more or less give us the structural, being able to learn what the stresses and displacements are due to some sort of load. But to keep in mind, we do have other tools like SOLIDWORKS plastics, where maybe your concern is this injection mold. You have problems with your tool maker that your wall thicknesses are too thin and you keep getting short shots. Well, you can eliminate that back and forth by running this analysis through SOLIDWORKS plastics to visualize and see whether you're going to have this problem beforehand. So it's giving you those tools at the design level, and you don't have to be an analyst or anything like this. All these tools are really intended for the designer, right? So, um, why specifically use our tools? Why specifically use FEA? Well, again, these things are in the family, nested within the SOLIDWORKS CAD. And hopefully you're having a good experience with the CAD where you're easy to pick up, easy to use. It's a pretty short learning curve. Well, simulation is the same. It's all embedded within the same CAD. It's integrated within there where we can do these fast turnaround changes to the model where, what if I change the material? Or what if I do increase the thickness of the model? How is that going to affect my overall results? If we didn't have these tools, we're not necessarily replacing prototyping, but hopefully what we're doing is reducing the amount of prototypes that we may need to do to learn what these changes are, how they're going to affect our design. And again, ultimately, we're a single source solution where we offer all those things that I mentioned earlier: training, support, consulting. We're going to be the resource for all these different tools for you along the design process. So I always like showing this slide here because because there are different versions of this simulation product for the structural side. I like showing the breakdown here. So the structural tools come in 3 different flavors. So the FEA tools come in 3 different versions: simulation standard, professional, and premium. So as we increase the level, you get more capabilities. So simulation standard gives you the starting point of just doing a linear static analysis for parts and assemblies. So we're able to test to see how strong it is, what the stress and displacements are, as long as we assume that we're not going post-yield. We're only living in the linear range of a material model, if you will. Right? So we'll talk about that as we see the example. You also get a fatigue analysis. So the fatigue analysis leverages the information from the linear static to be able to see whether it's going to fail after a certain number of cycles. So you get a pretty good starting point here with simulation standard. Of course, that's not going to solve all your problems, or you may have different needs. That's where simulation professional and premium come into play. Simulation professional gives you specific niche study types, like if you just wanted to know what the resonant frequencies are, or if you had like a steady state thermal problem, and you just want to do a quick check to see what the temperatures are, you can run this FEA approach thermal analysis. Or maybe you're dealing with large structures and you want to see whether your large slender structure is going to buckle, or you want to know how much load it can take before it potentially buckles. So you see how there's different unique study types that we can do within simulation professional. And there's also great tools here to talk about to be able to help you in optimizing your design. So we can specify different parameters that we want to change, set specific goals that we want to meet, and you can have the tool kind of adjust those parameters and help you find a better design, right? Simulation Premium gives you everything you see on your screen. So that is allowing you to do more advanced study types, dealing with more complex material models, like being able to run a nonlinear analysis. Now we can see what the stresses and displacements are post-yield. So being able to possibly run an analysis on softer materials like rubbers, soft plastics, things like that. So being able to get a more realistic answer with more complicated materials. The other study types like time history, harmonic, random vibration, shock, those all fall in the family of a linear dynamic analysis, which is allowing us to do these dynamic loadings, these more complex loading conditions where maybe a load is striking the model at a very fast instance or a very quick time, where we want to see how those stresses develop through that pulse loading. Or maybe you're trying to replicate something like a shaker table where your load input is changing, your acceleration is changing as a function of time. Or maybe you want to do some sort of seismic activity type of loading. So these are more complex loading conditions that we can do within our linear dynamic studies that are available within Simulation Premium. Right, so that's a pretty large scale of the types of problems we can solve, but definitely very easy to use. Once you're familiar with one study type, the setup becomes very familiar, becomes very easy to set up with those more complex studies. So as far as what we're going to discuss on this second scenario here, like being able to use those FEA results is, you may have noticed the model, it's the filter and the neck kind of bolted together, and we'll be showcasing how we can easily auto-convert those bolts to virtual bolt connectors if you're using a toolbox. Being able to, more importantly here, being able to transfer the information from flow simulation into our static analysis here, and then being able to see what information we get from those virtual bolts. And then we'll throw that into a fatigue study and want to see whether it's going to survive after 10,000 cycles there. Okay, so let me get into the interface here. And I am using SOLIDWORKS 2018, which is the latest version that's out here. And again, we're looking at the model that was created from Damon, or at least he was the first one to really run an analysis on this. And you see that we have the neck, we have the fuel filter here, or filler here, and it's bolted together, and there is a rubber gasket in between. So ultimately, what I want to do is see, how, based on those temperatures, am I going to see any weird stresses, any weird expansion that's going to happen into the model, the gasket. I just want to see what that behavior is, because I may have some sort of stress criteria that I don't want to exceed. Definitely don't want to exceed the yield of the materials itself. So I want to be checking for those type of elements. So right now, what you're looking at is the flow interface. So right now we're in flow simulation, and this is kind of where Damon left off, looking at those results, seeing what the flow patterns are. But the next thing that you need to do now, if you wanted to use those thermal results into a structural analysis, is export them to simulation. So in flow, all we would do is just go into our flow tools here. When we go to tools, we have this option, export results to simulation. And once you click that option, it just tells you that those results have been exported, and you can now import them, or at least attach a file to them into the structural analysis. And that's all you really have to do. All right, so after you select that option, we can turn on simulation. And then you're just going to be building up the study within that interface now. All right, so let's check it out here. So and you see, once I turn on simulation, all these options come up. It comes up in your command manager, and ultimately you get the option here to create a brand new study now within the simulation interface. So when I create a new study here, you see, depending on what license type, you have a variety of different options in terms of what you can choose as far as what you want to learn from the analysis. Here I'm just going to do a very basic static analysis. But you notice that we have some actual physical bolts, physical fasteners here, and they were actually used by Toolbox. And I understand that not everyone uses the Toolbox library, or maybe you don't have access to that. But if you do leverage that, if you are utilizing the Toolbox, we do have this option here before you create the study, is to convert Toolbox fasteners to bolt connectors. And that's very helpful because, typically what we recommend, especially when we're in a training, I recommend, not including those fasteners because, typically all those fasteners are really doing is just saying that those, components are being held together, of course. But the concern may not specifically be in the bolts. It may be, within the actual model itself. So really what you want to save time on, or help the solver a little bit, is getting rid of those little small components where, it's going to eliminate not having to mesh those components, or you're not having to define contacts for them. So you're making the solver run a little bit more efficiently by converting those bolts to virtual bolts. And I understand that there may be a situation where you may need to know what the stresses and displacements are of the actual bolt. And in that case, you may have to model those in and include that within the actual analysis and define the proper contacts. But you see that once I check that button, or check that option, and I accept the study type that I want, you may have seen that it ran a quick check. It's telling me here that it found 4 bolt connectors, and it took about a second to actually convert. So when I hit OK, you visually see that you do see the component there, but the blue is the virtual bolt. So it's leveraging the information from Toolbox as far as what the strength data is, what type of bolt you want that you're going to utilize. All that strength data is being transferred over into your simulation very quickly. If you didn't have that capability. And you see that when I expand my feature tree here, all those components that would have been included in the analysis are now in this auto-converted folder. Now they're not being used within the analysis, but it is being recognized by the virtual bolt. But what I was going to mention is, that's perfect role. That's assuming that you are going to, or that you do use Toolbox and you do have that option. So in the event that you don't, you of course have the option to define what these bolts are manually. Right? And the way we do that here, and I just suppressed them, but we just can go into our connectors here. You see that we have these different options to virtualize. You may not necessarily want to model a spring or a pin or a bearing, right? And these are ways to account for those, how that's going to affect the model, but not physically have those components in the analysis. So when I go into the bolt here, you see that we choose the specific bolt, whether we want like a standard kind of bore with nut or just a countersink with nut. So you see the different options that are available to us. And then once you choose a specific one or the appropriate one, you then choose the actual references as far as where that model is going to be attached. So let's go ahead and say that we wanted to do a, let's see here. Let's do one with the nut here. So just stay with the default, or excuse me, this one here. So let's say we had a countersink with nut. So I would choose a specific face, or in this case, it would be an edge. So I can choose the edge of where that bolt head is going to be, and then I choose the edge of where that nut hole is going to be. So I can then choose the opposite side here, and you see that is recognizing that there's components there, or that it's going to want to put that virtual bolt through those three components, and then you can adjust what your head diameter is, what your shank diameter is. You see that it transferred over what I had defined the material from the model, but you can definitely change what that material is. So it updates kind of the stiffness of the model, or you can specifically say, what the thread count is going to be, or what the actual physical bolt strength is going to be overall. So this is information that you may have from a data sheet of the hardware that you're using. You also have the option here to define some sort of preload. So all that information that you would typically get from an actual bolt, you can apply that here. And when you hit OK, let's say I want to do 30 Newton meter torque here, preload, can hit OK, and then you see that we get the actual bolt connector. All right, so even if you are doing this manually, it's not really complicated. Doesn't take long to set up. The longest thing that would probably take if you have a lot of holes, right? So, and then you see that it's nested here under the connections. You always have the option to edit it, to change something about the concept here. And then, so I can do that for the other three here. But moving forward, we would just then set up how this would be restrained in real life. So of course, we need to apply some sort of fixture. In this case, this is, excuse me, in this case, let me hide this component here. These are the lids from the actual flow study. But you see that the model actually has threads. But ultimately, what we can assume with these threads is that it's going to be restrained at those threads. Right? So, and you see that there's a lot of thin walls there. And really the concern here is the mesh, like trying to mesh those thin edges. You want to get a good resolution, and ultimately all you want to say is it's restrained within that model. So we can get rid of those threads and then just fix, add a split line, add a split face within that region, and just fix that face. So you see that we can kind of leverage the technique, or leverage the techniques of the CAD, being able to utilize those CAD features and utilize the fact that simulation is integrated within that CAD to be able to help us set up this problem. So let me activate the configuration that has what I just mentioned. So here we're looking at this FEA configuration. If we're looking at this model here, you see that there's a split line, and all I did was just say I want to split the face within that region here, and I was able to do it with just a plane that's intersecting through that model, and it's pretty much the face is covering where those threads are. So now that I have a split face, I got rid of those threads. I can go into my study and I can say, well, now I just want to fix that specific region. Right? So again, you can see how we can utilize the features of SOLIDWORKS CAD I don't have to go launch, re-import it into the CAD. I don't have to do all these things. I can just jump to that tab, make those edits, save them, and then use them in this new study here. Right? So really easy to use there. But the main important thing is, well, how do I use the information from flow simulation to this model? So you already saw kind of step one, which was exporting those results to simulation. But since I specifically want to export the temperatures, the temperature distribution that's happening within that model, all I have to do here is right-click on external load, and you see that I have this option, thermal effects. You may also notice that I have this option of temperature. Well, what does that mean, or how does that differ? Well, if you go directly, let's assume that you didn't run the flow simulation analysis, and we just choose temperature. You see that I can select faces, or I can select the individual bodies, and I can say that this specific body is pretty much has a temperature of, let's say, 120 degrees. What you're assuming here is you know what the final temperature of these components are. So, and you may not know that because there's a lot of things that may control the temperature. Maybe it's sitting outside, you have natural convection, or maybe you have a fan blowing through it, or through it where it's cooling it off. So what flow simulation is going to do is being able to get the final realistic temperature distribution due to all those different events that are happening. So that's where we can run. Stage one would be running that thermal analysis within flow and then utilizing that into simulation. So that is really the difference between the temperature and being able to transfer those results from flow. But when you go to thermal effects, which means that we're going to export those results or utilize those results from flow, when you select that, all that does is we get the simulation properties. So the properties of the study, and it specifically goes into this flow thermal effects. You see I already have something already tied into flow, but all we do is switch it to this temperature from SOLIDWORKS flow simulation. And what that means is I'm going to browse to my flow results, choose this FLD file, and that's where those temperature results are saved. So when I run the simulation study, it's just going to cross-reference that information that's in that file to be able to see what the stresses and displacements are due to that temperature, right? So we have that information here. We then specify what the temperature at zero strain is, which is the starting temperature, if you will, with zero deformation. So kind of the starting point there. And then that's it. You did part one already with the flow simulation. All we need to do is just transfer those results. So when I do that, you see that I do get this thermal here. That is my thermal loads referencing that result file. And then I can set up any additional things that this model may endure. In this case, that's my only load condition, but I may have some sort of external loading that's happening. You can add more to this. Right? You're not really limited to how you can set this up. You just want to make sure that it's reflecting correctly or accurately to what's happening in real life. All right, so once we set that up, we can mesh the model. Right? The nice thing about this mesh, about this global mesh here, is that we can specify, we can kind of just give it this default value here as a starting point, but we have options to refine or coarsen up the mesh throughout the entire geometry. We also have options here to apply a mesh control, which is being able to refine the mesh in a specific location of the model or a specific component of the model, where maybe that's our concern and we don't want to globally refine the mesh. We want to refine the mesh in the areas that we care about. Right, so once you mesh the model, we get something like this. So let me show you this here, where it's breaking down the model into these small elements. Right, and you see that globally it's auto refining in those small curved faces there based on the option that we selected. If we wanted to, we can refine the mesh for the gasket there. But once we have the actual mesh, we can run the analysis and get our results like so. Right, and ultimately, what we get is displacement. Then from there we can get strain and then stress. Right? So when we look at the stress is due to this thermal distribution. Right? So you see that really where the stress, and you may have already expected this based on how this was restrained, but the stresses are happening mainly at the bolt areas here. It pretty much is wanting to expand and want to separate from each other. You see that it's happening at these fillet areas as well. And ultimately, what you want to do when you get these stress results is you want to compare what the max stress is to the yield strength of the material, right? So, the main concern here, and I didn't show this, but what we're looking at here is an aluminum 7075 T6 material here for the neck and the nozzle, but the gasket is going to be some rubber, right? So we may be concerned about just that interaction between that very soft material to this metal here, right? And ultimately, we can look at what the yield strength is here of that rubber, and we're looking at 90 MPa, right? And somewhere in the model, there's a pretty high stress, but what we can do is we can edit the definition of that stress plot, filter out that gasket component if that's what we were interested in seeing by going into these advanced options and choosing that component here. So I can choose it graphically, and then showing what the min and max stress range is for that specific part alone by selecting this option here. So when I hit OK, it isolates that component, and you see ultimately, overall, it's seeing a high stress of only for about 5 MPa. So it's well under the yield strength of this material. So I can assume or conclude that, again, if this was our concern, that it has not yielded. It's not expanding to the point where this thing is stretching out so much that it's going to start tearing or anything like that. It's well under that yield point, so that gasket has survived. So we can do the same thing for those exterior or for those additional components, right? We can generate a new plot that kind of shows us the overall model again, a new stress plot here, and we can isolate those individual components, right? We also see that where that high stress is located, we can pinpoint that by turning on an annotation, letting us know that it's somewhere within the model here, right? And you see that there's some weird stress happening there. At this point, I'll tell you straight on, there is a stress singularity there. And it's pretty much what that means is there's some sharp corner that's happening within that model that we may want to update the geometry through some sort of fillet or curved face, right? But ultimately, the way we want to interpret these results is, we're not seeing that in these other areas here. And this model is somewhat, or at least this piece of the model is somewhat axisymmetric here. And we can kind of conclude that that's kind of an artificial stress point there. But we have tools within simulation where it can help us kind of determine that. So you see that when I go into my result folder here, I can right click on the results and we see that we have hotspot diagnostics. This is a new feature that was added a couple versions ago, but it's letting us know whether any if there any high stresses that are happening within the model are real or not. And it's actually telling me here that some hotspots were detected. So when I hit OK, you see that it's showing me the areas in gray, and it's a little bit difficult here as far as where those hotspots are. But if I isolate those, it's happening, at that area of where that singularity was. So kind of along here, right? And you see that all that really means is that we may need to adjust something about the geometry. But again, we have this nice feature that's letting us know whether we have a real stress or an artificial stress, and then we have techniques to relieve that. But everywhere else in the model, everything seems to be okay. You see that the stresses that are happening within the overall geometry, we're not expecting too much. Right now we're just gauging it based on the color scale. But if I specifically wanted to know what the stresses were at a specific location, I can go into my stress, go into the probe, and start clicking everywhere that I'm concerned about. And you see that it just gives me these probe labels here. And again, we can compare those specific areas to the yield strength of the material, right? And everything here is generally about under 200 from what I'm seeing or what I selected. And if I look at 200 MPa, and if I look at the yield strength of one of them, of the metal itself, you see that the yield strength for this specific metal here is about 505 MPa. So again, the overall model is well under the yield point. This high stress is pretty much an artifact, is not really real, but we can use that hotspot diagnostics to let us know that it's not real, but everywhere else will be okay based on the setup of the model, right? So again, the main point here, the main takeaway was how easy it was to transfer those thermal results based from flow simulation and integrate it within our thermal analysis. But we can make good design decisions by, how recognizing how to interpret these results and being able to really see how we can collaborate with both study types, both functionalities into this one analysis here. All right, so we can really, we're looking at the wrong plot here, but ultimately, we see that this is going to survive, right? Pretty nice here. So at this point, I may be, satisfied with the model. If we did see that we were seeing some high yield or high stress areas, it'd be very easy to go back to the geometry, adjust something about that, and not have to reset up the analysis, not have to redo everything. We can just make another configuration, link the simulation study to that configuration, and that's it, right? The last thing here, or the next thing that I want to show you, is right now we're just looking at a linear static analysis, but there may be a situation where we actually may need to run a nonlinear analysis, and it's always been the question here of like, when do I run one versus the other? Well, it's always a good starting point to see whether your study is going to work in a linear static analysis, or in a very simplistic way, a very simplistic study with those assumptions, right? The assumptions again of a linear static is just small deformations, flows are being applied slowly and gradually, where we don't have control of the time step here. But when we should graduate to a nonlinear study is when we are dealing with large displacements, when we are expecting the model to deform, a lot more or beyond, what we would get from a linear static, or maybe you are dealing with actual nonlinear materials. And in this model, we actually did have some the rubber gasket, where we may want to run that in as a nonlinear, but ultimately in this case, it fell under yield, so we were okay with that linear static. But sometimes you're dealing with more complicated metals, softer metals, or rubbers, where we can apply this hyperelastic material for dealing with rubbers, but ultimately being able to define what the stress strain curve is or what's happening post yield, so we can see what the true stresses and displacements are that are happening post yield, right? So the last bullet here is what would classify as a nonlinear analysis is kind of what the animation that you're seeing is, whether your contacts are changing as the model is changing, as the model is moving. So pretty much, the best example here is like a snap clip. You're clipping in, you see how those faces on the ends there are changing or are moving as I'm pushing in the actual model. So we wouldn't be able to do that really in a linear static capability, but you see that we can pretty much define or specify what the movement is in this time function and seeing how the stresses develop as it's actually truly snapping in. All right, so that's where the line is between linear static and nonlinear. If you've been to any of the other webinars, I did a more extensive webinar as far as what the difference is and when to know when you go from linear static to nonlinear. So you can check that on the YouTube channel as well. Should be available there. But the next piece of this here, as far as our analysis, is okay, we were able to see that it survived within that instant as far as what the thermal loads were. But will this fail after a certain number of cycles, after a certain number of uses? And that's where we would be able to want to run a fatigue analysis. And fatigue analysis allows us to check for this high cycle fatigue, which means that the uses that are running through your actual system range from 1,000 to 1,000,000 cycles. So anything lower than that is more considered low cycle fatigue, which we can't really accurately account for within our software. Right? And then what a fatigue study does is it references the parent study of the structural analysis, so the static analysis, and it cross-references that with an SN curve that you incorporate into your material database, and it's checking for the alternating stresses that are happening, and it cross-references that with the number of cycles to failure. And what you get is, as a result, is how long will this survive for, and how broken or how damaged the model is after the certain number of cycles that you specify. Right? So it's a really easy workflow, pretty consistent from study to study, but that's ultimately what we want to run here. So when we go into our SOLIDWORKS here, I can create a brand new study and specify a fatigue here. So when I choose fatigue, I can hit OK. And you see that my simulation tree doesn't really have much to define. All I need to do is define an event. So I'm choosing or I'm specifying how many cycles I want to account for. And maybe I want to do 10,000 cycles, 10,000 uses, if you will. And then we choose what the loading type will be, fully reversed or zero-based. Zero-based is more like a pulsating type of activity. So you apply that load, and then the load gets released or gets removed. So and then the model goes back to its original shape. You apply that load, you remove it, and then it's kind of that up and down type of behavior. Fully reversed is almost saying that you're kind of yanking on it, that you're applying a load in one direction and you're getting some min and max stress within that model, kind of equal and opposite, applying that load back and forth, if you will, right? As opposed to applying that load and then removing that load. So in this case, I'm just going to assume this zero-based type of activity that, it's not constantly running, or it's only running after a certain number of times, but then we're shutting off the fluid, or, it's kind of that on and off type of activity. And then we reference what study we want to, reference the stresses so it can determine what the alternating stresses are. So I choose the study name there. And when I hit OK, it then shows me what materials, or, it incorporates the materials from the static analysis. And you see that I chose a material here that had an SN curve, the 7075 T6. So it's utilizing this SN data to be able to tell me whether it's going to fail, or how it's going to do after a certain number of cycles that I determined, that I specified, right? But ultimately, you're defining the number of cycles to failure and the actual alternating stresses. So you can create your own SN data here, and then when you run the analysis, let me just snap to my completed set here. When we run the analysis, we get two plots when we run one event, a damage percentage and a life plot. And really what this is saying here, if we look at the life plot, is even though I'm trying to account for 10,000 cycles, you see that the overall model is going to survive well beyond 10,000 cycles. So really the minimum number of cycles that it will survive is about 127,000, which is happening where that singularity would be. But again, how we would interpret this result is, because we know that that's artificial, it's going to skew the results a little bit. But everywhere else where we determine that those stress results were okay, it's going to survive those number of cycles. And even in that singularity, it's still going well above 10,000 cycles, right? And that's how we would interpret that result. So pretty much I'm confident that this is going to survive 10,000 uses. So if I go into my damage plot, it's based off percentage, and you see that the max is going well above 100%. So 100% damage would mean that the model completely failed. It's broken. It didn't survive, those 10,000 cycles. But for those 10,000 cycles there, let me change this out of scientific notation so you can easily see what the number is here. So you see that the max damage of this, it was only just under 8%. So after 10,000 uses through that thermal loading that we've applied from flow simulation, this is going to survive. This is pretty much not a concern, right? And you see minimum here, 0.25%, that's the entire model. So we're well under as far as how broken this model is going to be. And even more so, you see that the damage percentage is happening at that singularity again, right? But everywhere else is pretty much blue, which means that it's going to endure zero damage, that this is going to survive well over those 10,000 cycles that I accounted for. Right, so this is a really simplified case. You may have a more complicated model, but ultimately that's how we interpret those results. And you see that it's cross-referencing that with the initial static analysis, where that static analysis, again, is referencing the thermal results from flow simulation. Right, so you kind of see where all those dots were connected throughout this design process. And that's pretty much it. That's all I really wanted to show you in terms of the technical side, as far as what this second stage may look like. But again, we offer the different tools to be able to go from stage one. My main concern is fluid flow. Now I want to see how that fluid flow is going to compromise my structural design. All right, so hopefully that wasn't too bad. Again, let me know if you have any questions within that. But the last thing that I'm going to close us off on is, again, we talk about this day in, day out, this, all our simulation tools. We have tons of resources out there for you. Definitely leverage that, if you're on subs and all that, or even if you're not on subs, we can, help you kind of gauge a plan or create a plan as far as how we can help you out within, either getting our tools or how our tools are going to be able to help you with your design, right? As you can see there on the bullet points, we have, several engineers here, degreed engineers that are, mechanical, aerospace engineering, combined, 40 plus years of just simulation experience, whether it's with the tool or just you running FEA on, real life components. We have a pretty large array of different experience levels here that we can help you out. So definitely let me know. Shoot us an email, contact your sales rep if there's anything that we can help you out, whether it's the CAD or the analysis side of things. But to conclude, we just kind of concluded stage 2 here, which is the structural and fatigue analysis. So again, being able to see how those two interact with each other. The third stage, which is what we're going to talk about next week, Tim Milo is going to present on simile abacus. So there may be a need there to run a more advanced structural analysis to really see, okay, if we were to apply a more extensive load or a more complicated loading condition, how is this going to fail in terms of like a more complex, how are those bolts going to fail? Or, what if we did want to include those bolt patterns or the actual physical bolt? We may need to actually include a more realistic type of scenario where simile abacus is really almost replacing real life testing. So it's a more advanced analysis tool to be able to run a more complex nonlinear analysis, or some sort of large displacement, or pretty much seeing this thing crush, or more realistic results, more complicated results in this multi-physics tool. So that's really what he's going to showcase there, which may be the third stage that you may want to run to check whether your design is going to be okay. All right, so stay tuned for that. Again, that's going to be next week, so definitely register for that. There's going to be some interesting stuff that we can do with that tool, but it kind of concludes as far as what we can, the third stage of this analysis set of this design. So again, that's going to be next week, Wednesday, May 30th at 11 a.m., just like today. And again, I'll be around here for a few minutes. So definitely shoot me a chat or let me know if you have a question, and I'll be more than happy there to answer them. If you do have some questions after the fact, feel free to email me at silviop@hawkridgesys.com. Or if there's something there that was interesting that you may want to see an actual demo for, feel free to contact your sales rep, and we can definitely set a demo up for you there. All right, so thank you for your time there, and hopefully I'll catch you on another webinar.